Okay, good morning, quantum enthusiast. Today we're going to kind of talk about something quite related to what we talked about last time. Last time we talked a lot about a game where you're trying to distinguish between two quantum states, two qubit states. So there's two qubit states you have in mind, at some angles, and you're given like a qubit in some unknown state, but you're promised that it's one of these two. You're trying to guess which one it is. Today we're going to generalize that a little bit, or look at a variant where we'll see eventually it's like about distinguishing between two rotations, two mystery rotations. So they're quite similar problems, but there's going to be a difference in the answers. And in fact, this tiny problem of distinguishing between two rotations will eventually lead us to maybe the most important subroutine in quantum algorithms, this thing called rotation estimation or phase estimation, which is at the heart of all the quadratic speedups in quantum computation, and even the speedup for the factoring algorithm. So even though it looks like just like we're looking at some toy problem, this is really the beginning of an extremely important quantum primitive. Okay, so this is what we were talking about last time, this problem of distinguishing between two qubit states. And we saw this situation where, if their angle between the two states you're trying to distinguish is 90 degrees, that was like the tests your mom and your dad gave you, then this was doable perfectly. You could just measure in the basis of these two vectors, and you'd win 100% of the time. And then we looked at the other version of the test where it's not just 90 degrees, maybe it's like 60 degrees, and we saw that you can do a reasonable, albeit not a perfect job of distinguishing these two states. And we saw there was different ways you could think about the error, the false positives, the false negatives, and so on. And one thing we saw is that if you allow so-called two-sided error, where you can have false positives and false negatives, then you could get a pretty good bound of 6.7% or something for both kinds of failures. If you're a bit stricter and you wanted so-called one-sided error, where maybe for one of the two possibilities, like false positives, you wanted to never have false positives, then you can make the false negatives be as small as 25%. And that was okay. And then finally, we considered a really challenging example, the one from Lawful Evil Corp, where it's a really tiny angle between the vectors. And we parameterized it as pi over n, where n is a big integer, 100 or 1,000 or something. Some teeny tiny angle. And this was very challenging. And we saw that, if you want, let's say, a one-sided error algorithm, your success probability was super small. Your success probability was 10 over n squared, which is tiny. But, all was not completely lost in the sense that, from here up, we were talking about this test where you get one copy of this qubit, you can measure it, do whatever you want on it, and then you got to guess. But we also thought a little bit about what if you could ask for lots of copies of the qubit, and you could do a measurement on each of them. Then it's kind of similar to a game where you have some action you can do that succeeds with probability 10 over n squared, and if you can repeat that action n squared times, then you actually get a reasonably high probability of telling the difference between this vector and this vector. Okay, so I want to get into it a bit more for now. Because here, really, I told you algorithms. I said you could do, perfect. You could get 25% error here. You could get 10 over n squared error here. And I want to kind of try to convince you that these algorithms we saw are actually the best algorithms that you can do. That it's not like we just came up with some dumb algorithm and there's something smarter. For example, in this case, I want to convince you that the best error you can achieve is 25%. Okay? And it's pretty intuitive, and I'm actually going to mostly leave it to homework, but I'll sketch some parts of it here. So here's the setup. You have two vectors, unit vectors v and w at some fixed angle theta, and you know these vectors. There's a picture over here. But then you're given a qubit in an unknown state, which we'll call test, and we're trying to decide, okay, is test v or is it w? And for this discussion, I'm going to make it a requirement that you have to have one-sided error. Oops. And I can even pick the side, so no false positives. Although, it's symmetric between v and w, so I arbitrarily chose v to be the one where you're supposed to say yes, and w the one where you're supposed to say no. Doesn't really matter. Okay, so this is just part of the problem. I'm going to insist that you have, one-sided error, and then the question is, like, how small can you get the other kind of error? So what's the lowest possible error probability? And that's for, I suppose, false negatives. Okay. And the last time we saw this idea, this was our idea for the algorithm. It was a measure in the basis, we'll call it W, and W perp. This is just the name of a vector that's perpendicular to W. Okay, like depicted in purple there. Okay, and say yes if the outcome is W perp, else say no if the outcome is W. Okay, and we saw that this has like no false positives as desired. So let me try to remember what this means. This means, I suppose, that you never say yes when the true answer is no. So that's like you never say yes when test happens to be W. And this is the one you're saying yes on. So it's like saying you will never get this measurement outcome if the true vector is this red W. And that's true because like this angle is 90 degrees. So if you measure in this basis, and the true vector is W, you'll 100% see W as the outcome. But it has some false positives, and the probability of, or false negatives, I'll just say error, when the true vector is V. Well, that's like you imagine the true vector is V, and you're hoping the measurement outcome is this one, and you get an error if the measurement outcome is W. So the probability the measurement outcome of W is W when the vector is V is cos theta squared. Okay, cos theta squared. Okay, and what that is depends on theta, of course. And what I kind of want to argue to you is the following claim, that there's no better algorithm. In the sense of still having no false positives, but making this probability smaller. And it's not too hard to prove. And as I said, you'll kind of investigate it on your homework. The main idea behind it is, you could try to imagine like some quantum code that like takes test and like does some stuff to it, like maybe rotates it or reflects it. But like, the fact of the matter is that somehow, like, even if you rotate this picture or reflect this picture, like, the angle is always theta. Like, you cannot change that. Every operation you can do is unitary. You can't change the angle being theta, so there's not a lot you can do. And moreover, this requirement that you actually have absolutely no false positives also means your hands are really tied. Like, if the true vector is W, then you have to say W 100% of the time. So kind of like any measurement you could do that has like some probability of this or some probability of that, basically one of those probabilities has to be 100%, because if you measure something with like, and like there's a 90% chance of this and a 10% chance of that, then like how are you achieving some outcome 100% of the time? So this is basically the ideas, but let me say a few things that you have to like take care of, and actually definitely verifying that this is the case. So let me say, like, even if you can, like, take test and not just measure it right away in the basis, W perp. You could, like, rotate test or reflect it. By doing some quantum unitary operations. But as I said, that kind of just changes the picture to, like, a different picture with angle theta. But here's another creative thing that you might try to do, which maybe you didn't think about, is you could like add some new qubits. So you have this one qubit, you could do the following. You could like do new qubit, and now you have 2 qubits. And now you could do some, quantum operation on both of them. Like you could do if this one, then toggle that one. Or you could add 2 new qubits, and you could do like if A and B, then toggle C. And maybe that would help you. Maybe you'll do extract all at the end, and you get like 3 bits of information out of your extract all. Maybe this could do something. Turns out no, but you have to think about that a little bit. So you could do new qubit, then like do some unitaries or quantum operations in higher dimensions. But it turns out this still doesn't really help you. And again, the reason is basically, even if you like take these states and like add qubits to go in higher dimension, they're still at angle theta. And if you do a unitary, as we saw before, unitaries preserve angles, so they're still at angle theta. So somehow it doesn't really help you. And maybe there's one more thing you could try, like you could imagine, is you could use classical randomness. Like you could decide, I'm not going to be a deterministic algorithm. Like the first thing I'll do is like I'll use like a random number generator to like pick 10 random bits. And if they come out this way, I'll try this algorithm. And if they come out this way, I'll try that algorithm. You can do it, but it still doesn't help. And the main reason there is like, again, this restriction is really strong. Like if the answer is W, if the true value is W, you have to say W with 100% probability. So like adding more randomness into the picture like doesn't really help you. Okay, so instead of trying to mathematically prove it, I've kind of left it a little bit to you and instead just tried to like berate you into believing this claim. But I hope it's pretty believable. Okay, any questions about that? Okay, let's pass out the tickets. Aaron. Thanks. Okay. So, good. So what I'm saying here is that like this is the best probability, cosine theta squared, for this problem. And let's plot this. I mean, let's literally, as though it were 11th grade, we'll plot cos theta squared. Okay, so let's see. This is like the theta axis. There's 0. And this we'll call the, this is like the failure probability axis. This is for like one-sided distinguishing with angle theta. Okay, so let's have theta go from like 0 up to pi over 2, which is 90 degrees. And we'll just plot cosine theta squared. And it looks like the top of a cosine wave. Okay, that should go down to 0. Okay, this is cosine theta squared. This is 1. I suppose like this. It's like a half. It's like pi over 4, 45 degrees, and so forth. Okay, and it kind of ought to make sense. So like here, when theta is really teeny tiny, like your failure probability, your false negative probability is practically 1. And you can see even the curve is very flat here. So if you go out like, 1 over nth of the distance here, like the amount down you go from 1 is like 1 over n squared. And, particularly it says that the angle is 0, like if W and V are literally on top of each other, and then like I give you as like a prank, like a state, I'm like, it's either V or W, which are the same thing, and you have to guess whether it's V or W, your success probably is, you cannot guarantee yourself any success, If your algorithm, yeah. Conversely, this is like, with your mom and your dad, when you get like 2 vectors at angle 90%, you can have failure probability 0. Yeah. Good question. So if you were allowed 2-sided error, it could be a half. So like if you're allowed false positives and false negatives, it could be a half. Because you could say like, you know what, I'm not even going to look at the state. You gave me a copy, that's fine. I'm just going to randomly output a guess of yes or no. And then case 1, the answer is yes. You have a 50% chance of saying yes and a 50% chance of saying no. So your failure probability is 50%. And case 2, the true vector is W. You have a 50% chance of guessing W, so your failure probability is 50%. But here we're imagining the situation where like you have to have you're required to have absolutely no false positives. So that basically means if test really is W, you have to say W. Otherwise, like, this algorithm is not allowed. Which basically means there's only one legal algorithm for you to do in this case, which is to just always say, no, I guess that it's W. Because it could be W, and if it is W, you have to say W. So since it could be W, like in this setup, you're obliged to just say W. And then you do have like 100% chance of false negatives because like it could also be V, but then you're 100% of the time saying W. Good question though. Like actually, even as I was like explaining it to you, I was getting a little confused myself. So I'm glad you asked that clarifying question.